Do you know? Every 43 seconds, a child dies from pneumonia somewhere in the world. That is over 7,40,000 children under 5 who died in 2019 alone. And many of these deaths could have been prevented with faster diagnosis. Hi, I am Saurabh Singh and I have built an AI system that can detect pneumonia from chest x-rays in under 2 seconds. But here is what makes it special. It does not just tell you yes or no, it can actually show you exactly where the infection is on the lung. Over the next few minutes, I will show you 6 different AI models working side by side, give you a demo, and explain how we are pushing the boundaries of medical AI. Let's get started. Here is what we will cover today. First, the problem. Why pneumonia detection is harder it looks. Then I will show you what normal versus pneumonia x-rays actually look like. Next, I will walk you through the system architecture, the technologies and design choice that power its solution. After that comes the exciting part, a live demo, where you will see multiple AI models in action, including one that actually visualizes the infected area. Then I will explain we built it, the workflow, the model we trained, and their performance. And finally, where we are taking this project next. Let's jump into the problem. Pneumonia is one of the leading causes of death in children and elderly patients worldwide. Diagnosis is required chest x-rays, but here is the challenge. Manual diagnosis takes time. Radiologists can be overworked or simply unavailable in remote areas. And even experienced doctor can sometimes miss subtle signs. That's why we build an AI powered solution to help doctor make faster, more accurate decisions. For this project, I used a publicly available dataset from Kaggle provided by the National Institute of Health. It contains over 30,000 chest X-ray images divided into normal and pneumonia categories. This is real medical data, and our goal is to train AI model that can learn the difference and eventually help save lives. Now, let me show you what we are actually dealing with. Here you can see normal chest x-rays in two common views. Anteroposterior, which is front view, and lateral, the side view. Radiologists look at both angles to get a complete picture of what is happening inside the lungs. Now, compare this with a pneumonia X-ray. Notice the white, cloudy patches in the lungs area? That is the infection. That patches indicate fluid or inflammation, classic sign of pneumonia. To the untrained eye, these differences might seem obvious, but for an AI model, detecting these subtle patterns consistently across thousands of images is actually quite challenging. That is the problem we are solving. Teaching machine to see what doctors see, and in some cases, even help them see better. Before the demo, let me show you the system architecture. Streamlit frontend handles the user interface, model selection, image uploaded, and result displayed. It communicates with our FastAPI backend through REST API calls. The backend does three things. First, validate and pre-processes the uploaded image. Second, runs interface through one of our 6 preloaded models. Third, returns result with confidence score, and for YOLO V5 bounding box coordinates. I chose FastAPI because it's fast, asynchronous, and production ready. All six models stay loaded in memory for instant prediction. Everything is logged for performance tracking and continuous improvement. This architecture is scalable and development ready. The backend could easily be containerized and deployed on any cloud platform. Now, let's see in action. So, how does our system actually work? It's incredibly simple. Just three steps: upload, predict, and submit. That's it. First, you upload a chest X-ray. We support JPG, PNG, and medical DCOM format. You select which AI model to use and can even adjust the sensitivity threshold. Next, click Predict. The system analyzes the image instantly and shows you a color-coded result. Green for not pneumonia, red for pneumonia detection. Finally, you can submit feedback. Mark if the prediction was correct or incorrect. Everything gets stored into a table you can download for analysis. But here is where it gets interesting. We did not just build one model, we built six different AI models, each with its own strength. Let me show you the actual interface. Here is the UI we developed. On the left side, you can select which AI model you want to use. We have basic CNN model, our baseline model built from scratch, fine-tuned CNN model, an improved version with better accuracy, ResNet 50, a deep pre-trained model known for good performance, MobileNet V2, optimized for speed and mobile devices, DenseNet 121, another powerful pre-trained architecture, and YOLO V5. This one is special because it does not just detect, it visualizes where the infection is. On the right side, you upload the chest X-ray. We support JPG format, PNG format, JPEG format, and even medical DCOM format. Let's upload one image. Notice this slider? That is the sensitivity threshold. By default, it is set to 0.5. If you lower it, the model becomes more cautious and flags more cases as pneumonia. If you raise it, it becomes stricter. We'll keep 0.5. Once you upload the image, you can hit predict. Behind the scene, the Streamlit frontend sends the image to our FastAPI backend, which processes it through the selected model and returns the prediction in milliseconds. This API-based architecture means we could easily integrate this with hospital system or mobile app in the future. The result appears instantly color-coded for clarity. Green means not pneumonia. Red means pneumonia detected. We'll see pneumonia detection color in later. Below that, there is a feedback section. You can manually confirm whether the prediction was correct or incorrect. Click on Submit Feedback. All of this get saved into an editable result table, which you can download as a CSV file anytime. The system also calculates performance metrics per model, showing both technical accuracy and user agreement accuracy. Now, let's test this live with multiple models. Let me start with basic CNN model, our baseline model. I will upload this normal X-ray image. Leave the threshold at default and click Predict. Notice how fast that was? That is the power of FastAPI asynchronous processing. The image was sent to the backend, processed through the CNN model, and the result was written in under 2 seconds. There we go. Not pneumonia. With 75% confidence, probability is 25%. The image is indeed normal, so I will mark this as correct and submit. The result table update instantly. Now, let's see how the fine-tuned CNN handles the same image. We'll select the model, upload the same image, and predict. Not pneumonia, with 87% confident. Notice the improvement? The fine-tuned version is more confident and accurate. You can submit feedback. Model is updated. Now let me show you the pre-trained model. These are powerful because they have already learned from the millions of images. Here is the ResNet 50. Upload the same image, then predict. Not pneumonia. Confidence is 74%. And mobile net. This one is optimized for speed. Perfect if you want to run this on a mobile devices or tablet in a clinic. Upload the same image. Predict. Not pneumonia. 89% confidence. Even better performance than the ResNet and much faster. Submit feedback. One more DenseNet 1-to-1. We'll upload the same image. Predict. See, 90% confidence, not pneumonia. Click on submit. Let me upload an actual pneumonia X-ray. Starting with basic CNN model. Upload an image, leave the threshold at default and predict. Pneumonia detected, 95% confidence. See, color coded red color is correct prediction. We'll click pneumonia and yes, submit field. We'll test same fine-tuned CNN model, upload same model, same image, click on predict. See, 98% confident. That is better confidence. Yeah, it is pneumonia. Pneumonia affected in this area. Yeah, submit feedback. Now, next model is ResNet 50. Upload same image, predict. Pneumonia detected 69%. That is less confident. Yeah, but result is correct. It is pneumonia and yes, correct. Submit feedback. Now we'll test MobileNet V2. Yeah, MobileNet V2. We'll upload same image, predict. 72% pneumonia detected, slightly higher than the ResNet. Now it is pneumonia and yes, submit feedback. And next model is DenseNet 1-1. We'll upload same model, same image. Click on predict. Pneumonia detected 74%, less confident. Submit. Let's upload a new image and start with the basic CNN model. Okay, we'll upload this image. Click predict. There we go. Not pneumonia with only 29% confidence. But wait, this image is actually from a pneumonia patient with infection visible on the left side. So this is a wrong prediction. It is pneumonia detection and prediction was also incorrect. So I will mark this as incorrect and submit. The result table update instantly. Notice how the accuracy of basic CNN drops here. See, now it's 80%. This shows the system is tracking real performance. Now let's try the fine-tuned CNN model. With the same image. Predict. Pneumonia detected. 89% confident. That's correct. I will mark it correct. Pneumonia. Prediction was also correct. Submit feedback. You can see how different model handle the same image differently. The fine-tuned version caught what the basic model missed. Now, here is where it gets really interesting. Let me switch to YOLO V5 model. This model is different from the others. While the previous model just give not pneumonia or pneumonia answer, means yes or no, with a confidence score. YOLO V5 actually shows us where the infection is. Let me upload the same pneumonia X-ray. Click predict. Look at this. See these bounding boxes highlight a specific region of the lungs. The model isn't just saying pneumonia detection, it is pointing to the exact affected areas. This is incredibly valuable for doctors. It does not just a diagnosis, it is a diagnostic aid that guided them to the problem area. Yeah, this is pneumonia. Direction correct. Let me test a few more images to show you how consistent this is. The same model will upload, predict. See, 65% confident pneumonia detected. See the bounding boxes? They are highlighting affected area in the both the left and right lungs. That's pneumonia. Submit feedback. Okay, let's try another one. Predict. Pneumonia detected with 52% confidence. Again, bounding boxes on the both sides, left and right lungs clearly marked. Pneumonia and submit feedback. One more image. Predict. Pneumonia detection with 51% confidence. This time, notice the bounding boxes? Focused on the left side only, showing the model can adapt to different infection patterns. This kind of explainability builds trust in AI system for healthcare. Doctor can see what the AI is seeing, verify it against their own analysis, and make more informed decisions. I want to download these results. So I want to download as a CSV. So I will click here, and yes, this location I want to save. Click on save. It's downloaded. Okay, let's check. In this file it's showing. Okay, let me open. See. Yeah. Perfect. This is the power of combining object detection with medical imaging. That is the demo. Let's head back to the slide. So, why did we design the system this way? Here are the key benefits. You can easily switch between 6 different AI models to compare results. It supports multiple images formats, including medical grade DCOM files. You get flexible control with adjustable threshold settings. Results are color coded, making it easy to understand at a glance. There is an editable feedback table so user can correct mistakes. Everything can be exported as a CSV for further analysis or record keeping. And with YOLO V5, you get visual explanation, not just predictions. In short, this is not just a prediction tool. It is a complete system for diagnosis support, evaluation, and continuous improvement. Now, workflow and methodology. We'll cover UI flow diagram, model workflow diagram, model-wise performance comparison. Now, let's break down how the system works behind the scenes. Step 1, Model Selection. The user picks which AI models to use, from basic CNN to advanced YOLO V5. Step 2, Upload an image. They upload a chest X-ray in JPG, PNG, or DCOM format. Step 3, Predict and adjust threshold. After clicking predict, they can adjust the threshold if needed. The result analyzes the images and return a color-coded result. For YOLO V5, it also highlights affected regions. Step 4, User feedback. User can add feedback to help improve the system over time. Step 5, View performance. All prediction can be downloaded as CSV and user can view model-wise performance comparison side by side. This flow makes the system both simple for end user and powerful for researchers. Now, let's talk about how we actually build these AI models. This involved 5 key steps. Step 1, Dataset preparation. We collected over 30,000 chest X-ray images, validate them, and clean the dataset to ensure quality. Step 2, Data analysis and pre-processing. We performed exploratory data analysis to understand patterns, then pre-processed images through resizing, normalization, and augmentation to improve training quality. Step 3, Model development and saving. We build multiple models, basic CNN from scratch as our baseline, fine-tuned CNN for improved accuracy, transfer learning with ResNet, MobileNet, and DenseNet, and YOLO V5 adapted for medical image segmentation. Step 4, Evaluation and results. All models were trained using validation sets, then tested. We evaluated them using accuracy, precision, recall, and confusion matrices. Step 5, Deployment and integration. We integrated all models into a single interface for easy comparison and real world use. Each of these steps was crucial in building a reliable medical grade system. Now, let's look at the model wise performance comparison. Here we can see all our model side by side based on key matrices: accuracy, precision, recall, and ROC AUC. MobileNet V2 leads with 81% accuracy and the highest ROC AUC of 0.83, making it our most reliable classifier overall. DenseNet 1-to-1 and our custom CNNs also performed well with accuracies around 80%. However, notice the recall values? They are relatively low across all models, ranging from 27% to 47%. This means we are missing some pneumonia cases, which is something we need to improve in future iteration for patient safety. ResNet 50 struggled with this particular dataset, showing zero precision, likely due to class imbalance issue during training. Overall, MobileNet V2 strikes the best balance between accuracy and reliability, while YOLO V5, though not shown here, adds the critical visualization capability. This comparison helped us understand that no single model is perfect, which is why offering multiple options is valuable. To wrap up, this project demonstrates how deep learning can genuinely transform medical imaging. We have built a complete system with six different AI models. Our best performer, MobileNet V2, achieved 81% accuracy with a strong ROC AUC of 0.83, while YOLO V5 adds the critical visualization capability that doctors need. But let me clear, this is a support tool, not a replacement for radiologists. AI should help doctors make better decisions, not make decisions for them. Now, looking at the result, there is definitely room for improvement. Here is what I am planning next. The next step include improving model sensitivity, expanding to detect multiple lungs diseases, and optimizing for real-world deployment on mobile devices. The ultimate goal is clinical validation and integration with hospital system to make this a life-saving diagnosis tool. That's it. Thank you for watching my presentation on AI-based pneumonia detection. I hope this gave you a clear picture of what we have built from basic CNN to advanced visualization and where we were headed. This project combines deep learning, medical imaging, and real world usability, and I am excited to keep pushing it forward. If you have any question or feedback, feel free to drop a comment below. I will make sure to respond. Thanks again.